Welcome to the Foundation Engineering course. We were trying to talk about in our earlier classes regarding the soil exploration or the geotechnical investigation. And in today's class and in the next coming class, we'll be focusing on how to calculate the in situ stresses that gets developed in the soil, and particularly because of the external load which is coming from your structure. Okay, so due to the external loading what is coming from your structure, or because of anything else which is there above the ground surface, like it could be an embankment, or it could be because of your any moving load, or your dead load in the form of concentrated force, or a line load, or what is called as a strip load, a rectangular load, or maybe a circular load. So whatever. So due to those external loading, how do we calculate the stresses which are getting developed in your soil at different depths, a different position in your soil strata? Okay, that's what we are going to be talking about. Earlier in soil mechanics course also we have touched upon what is called as in situ stresses in the soil, but there the in situ stresses what we have talked about are due to the gravitational force only. That's nothing but due to the self weight of the soil, and in considering the flow condition. Okay, not just only taking the effect of your what is called as gravitational force, we have also looked into the conditions for flow through the soil. Due to the flow through the soil also, we have seen how the stresses are getting developed in the soil. In today's lecture and in next subsequent lecture, we'll be mainly focusing on the stresses getting additionally developed in the soil due to your structural load or any external load which is acting on the ground or which is acting on your soil. So let's quickly understand. Hope this particular slide, if you remember, we have seen in our soil mechanics course, where we said the complete stresses that are getting developed in the soil, that so-called stress distribution, what we are going to be talking in the soil, will be due to the effect of what is called as your self weight of the soil, which we said we'll be learning in soil mechanics course. And then subsequently in this particular course, what we'll be focusing on is how do we calculate the stresses that are getting developed in the soil due to your surface load. Surface load is nothing but the external load which is coming from your superstructure or any other force in the form of surcharge or whatever load which is directly acting on your surface of the ground or surface of your soil strata, what you are referring to. So let's start understanding how do we calculate the stress in the soil at any depth due to your surface load. So why this stresses that are getting developed in the soil due to the surface load is important, because whenever we are going to analyze the problems related to that of the compressibility of soils, that's nothing but your compression, what is happening in the soil, or the settlements what your soil is undergoing, or whenever you come across with the problems related to the bearing capacity of foundation, or stability of embankments, or lateral earth pressure of your retaining structures, in all these particular cases, because these are all your external structures due to which then there is an additional load coming onto your soil strata, because of which some additional stresses are getting developed in the soil, and due to that additional stresses there will be some additional amount of settlement what your soil would undergo or your foundation would undergo. So our ultimate objective is now to understand whether your soil strata on which your structure what you are trying to build is going to be safe or not, in terms of the settlements what the structure is undergoing, or in terms of the bearing capacity aspect of that particular structure. So what generally happens when a load is applied on your soil strata? Okay, so obvious that due to that load what you are applying on the soil strata or on the ground surface, you are going to see some additional stresses which are getting developed in the soil in the vertical direction. Okay, so what we are going to be calculating here is increment in stress. That's the additional stresses what are getting developed in the soil due to your surface load is nothing but we are going to be talking in the vertical direction. So due to the load what is applied on the ground surface or on the soil strata, how much additional stress is getting developed in the soil at any depth in the vertical direction is what we are going to be talking about. and that increased stress due to your additional load what is coming onto your soil or onto the ground, okay, that's going to be depending on the area on which that particular additional load or your superstructural load or the load coming from the foundation or any other external load what we are trying to talk about. So that load is applied on how much area, okay, whether that load is applied over a smaller area, whether the load is applied over a large area. So depending on that, the increment in stress what is getting developed in the soil would be depending on. And that so-called the purpose of, as I mentioned earlier, so the purpose of talking about this stresses due to the surface load is ultimately to understand how much additional stresses are getting induced in the soil, due to which how much additional settlement is happening, and what is your total settlement that is going to be happening in that particular soil. What is the total settlement in the soil or in the foundation or in the structure which is resting on the ground. Okay, so once I know what is your total settlement, so total settlement with certain factor of safety, if we divide it with, we get what is called as allowable settlement. How much settlement as per the standard design codes you want to allow in that particular structure. Maximally, how much allowable, how much settlement can be allowed in that particular structure, we'll be trying to understand. And for that allowable settlement, that for that amount of settlement what can be allowed in that particular structure as per the standard codes, what shall be the load which is permissible, which can be additionally transferred from that structure onto the soil to ensure that the settlements whatever are getting developed in that particular soil are within your permissible limit, or those settlements are what is called as your allowable settlement. So generally, whenever you come across with this vertical stresses, whatever that we are going to be talking about, so that would depend on how much is the intensity of your external loading, what you are additionally applying on the ground, and subsequently the area over which that particular load is being spread, in order to understand how much is that additional increment in stress which is getting induced in your ground. Foundations and structures placed on the surface of the earth will produce obviously stresses in the soil, because apart from the gravitational force, that is the self-weight of the soil, due to the self-weight of the soil already we have seen some amount of stresses which were getting developed in the soil. Now apart from that, in addition to that stresses, because of the effect of your self-weight of the soil, now due to the load coming from the foundation and due to the load which is coming from any structure like retaining structure or an embankment or whatever, so additional stresses are what is getting developed in your soil strata. These stresses will decrease with the distance from the load. So we'll try to understand what does this statement mean. So depending on the position where the load is applied and subsequently where we are trying to calculate the amount of stress that is getting developed in the soil due to that applied load. So what we understand is that as we move away from the position of that loading, the amount of stress what we get developed in the soil is going to be decreasing. And if we are nearer to the region of the load what is applied, then obvious that the stress what was getting developed in the soil is going to be relatively high. And we'll mainly understand how these stresses are getting decreased depending on the nature soil which is bearing that load, all that aspects we'll try to understand. If the soil is strong, then that particular soil will have more resisting capacity, or in the way more load carrying capacity. So automatically the stresses what gets transferred into the other deeper layers would start decreasing as the load carrying capacity of the above soil is relatively more. If the above soil is not carrying more load, then automatically that soil says, I'm not able to carry the load. So the soil which is there below has to take the responsibility in taking that particular load, whatever is getting transferred from your superstructure or from your foundation of that particular structure. So we will start understanding how do we calculate the stresses due to a concentrated load. So what do I mean by concentrated load? Let's say, for example, if you have your structure designed properly with loads properly distributed from the slab onto the beams and from the beams onto the columns, and from the column the load gets distributed onto the foundation. Okay, let's say when we are trying to look at the condition of a column, so the load what is coming from each individual column is considered to be what is called as your concentrated load, otherwise which is also called as point load. So we take your column load as equivalent to that of your concentrated load or point load, and accordingly we go on to understand, due to that point load, what is coming from the foundation onto the soil, because the column load gets transferred onto the foundation. From the foundation, the load gets spread over the area on over the area of the soil on which your foundation is in contact with that particular soil. Let's say if this is my foundation, and this particular foundation is resting on the soil strata like this. So load is coming onto the foundation, and the load what is coming onto the foundation from the column has to be distributed onto the soil strata. Where it is getting distributed onto the soil strata? On that particular contact area between your soil and your bottom of the foundation. So that's how the load first comes and then gets distributed, and subsequently it further gets distributed onto the adjacent soil particles. And that's how, as you go into the deeper depths, the area over which that particular load is getting spread is increasing. Why is it increasing? Because at the top, if you are applying what is called as, let's say this is my ground. Okay, on this ground you are applying some concentrated load or a point load of intensity, let's say P. Now what is happening when this particular load is acting on that ground surface? As we said, it's a point load, so we are going to have just a point contact between that loading and your soil particle. And what we understand is the soil grain which is there here will be subjected to a maximum stress. Why is it subjected to maximum stress? Because whatever the load that you are applying, who is responsible initially to take that load? That is that small particle which is in contact with that loading mechanism. Okay, so stress what is getting induced immediately below your application of that load is what we consider it as infinite. Why do we say infinite? Generally, whenever we talk about stress, we say in simple terms, force acting over the cross-sectional area. Now, what is the area of contact over which that particular point force is acting? The area of contact is a point contact. The area is relatively very, very small. So if we say area is relatively very, very small, then automatically the stress what we are calculating there for that point, immediately where your point load is acting. Okay, so there the amount of stress is relatively very, very high, and in general terms people say it is something infinity. Infinity doesn't mean it is something what you cannot define, but it's a relatively very high value. That's what it means. But as you move into the deeper depths, what is going to happen? How much is the intensity of the stress that is getting developed? So what is going to happen? This particle which is in contact with the adjacent particle will start distributing the load onto the adjacent particles, and those adjacent particles will start further distributing the load onto the further adjacent particles, and in the process, as you move into the deeper depths, you have got more number of soil grains which are responsible for carrying that particular P intensity force what is applied. So if you have more number of particles, in the sense the area over which that particular load is getting spread is increasing as you move into the deeper depths, and the force by area, as the area increases, automatically the stress what is getting developed in that soil at different depths continues to decrease as you move into deeper and deeper depths. So how do we calculate these stresses that are getting developed in the soil due to the concentrated load? That's nothing but your point load. We have got two different ways by which we can go on to calculate those stresses that are getting developed in the soil due to your point load. One is by Boussinesq's formula, and other is by Westergard's formula. And as of our course is concerned, our main focus would be with regard to your Boussinesq's formula, based on which we'll try to understand how the stress increment is existing, or how the stresses are getting additionally developed in the soil at different depths because of different loading condition, not just only for your point load. We'll be then talking about different other loading conditions also, because in geotechnical engineering, we don't only talk about your what is called as point load coming from the column onto your foundation. Okay, so we have different other types of loads also. Let's say, for example, if you look at your compound wall is my structure. So when it comes to the case of the compound wall, how the load is getting transferred from the compound wall onto the foundation. So what kind of load is it called as? that particular load is what is called as your line load. Why is it called as a line load? Because the width over which the load is acting is small, but the length to which it is extended, it is relatively large. Oh, sorry, I should not be calling it as a line load. Rather, the example for compound wall is called as your strip load, because the width over which the load is acting is limited, but the length to which it is extended is relatively large. So such kind of loading is what is called as your strip load, and that such kind of footing which is responsible for holding your compound wall in a stable condition, such footing is what is called as your strip footing. Okay, and what could be the classical example for your line load? Line load, let's say in the case of a railway track, if you look at your two rails which are running parallel to each other, load coming from individual rail, that horizontal member which is running, or your member which is running continuously, the load what is coming from that individual rail onto the ground, so that load is nothing but it is called as your line load. Line load in the sense, or a very small width, the width of the rail what you look at is relatively very small, so I can consider with that width it's a kind of a point load which is extended in the length direction of the rail to a maximum distance. So such kind of load is what is called as your line load. Likewise, if it is a rectangular footing, so automatically the load coming from that rectangular footing onto the soil is what is called as your rectangular load. If it is a square footing, the load pattern what comes from your square footing onto the soil is nothing but we call it as your square loading. If it is a circular footing, then load coming from the circular footing onto the soil is what is called as your circular loading. If it is an embankment, the structure what you are looking at is an embankment, then that particular type of load what is coming onto the soil is what is called as your embankment loading. Okay, so these are all different types of loadings what we are going to be talking about. So due to these different types of loads, how your stress is increasing in the soil strata is what we are going to be talking about. That increment in stress in that vertical direction in your soil strata is what we are going to be looking at due to the different loading conditions what we are going to be talking about. But however, when it comes to the case of this concentrated load, in the case of this concentrated load, we can go on to understand how much is your vertical stress that's developed in the soil due to this concentrated load, either by Boussinesq's formula or by what is called as Westergard's formula. Okay, so basis for any other load conditions, if we want to calculate the stresses that are getting developed in the soil strata, basis is going to be your stress increment expression what we are looking at, what we are going to be looking at for concentrated load. That is going to be the basic expression. From that only, for all other different loading conditions, the subsequent the stresses in the vertical direction are developed. Okay, as of our syllabus or our main focus is concerned, we'll be mainly focusing on our Boussinesq's formula, what is developed in the case of concentrated load, and then subsequently which is used in subsequent cases of other loading conditions also. And coming to this Westergard's formula, if I am correct, in the transportation engineering problems, you will be covering this particular aspect of Westergard's formula in analyzing the stresses in your pavement or analyzing the stresses in your ground in different layers of the pavement. If you are required to analyze the stresses, you will be following this particular Westergard's approach. So let's understand how to calculate your stresses due to the concentrated load and the basis from where this particular expression has come. Okay, so we are looking into the formula what is given by Boussinesq. Boussinesq is a scientist, okay, famous French mathematician and also a physicist who made a significant contribution in the areas of hydrodynamics, vibration, and light and heat. Okay, so he is not basically a geotechnical engineer or a civil engineer. So his basic fundamentals are from physics and mathematics. Okay, where his contributions are in the area of hydrodynamics, vibration, light, and heat. He is the person who is responsible in developing this particular stress increment expression, which is later what is called as your Boussinesq's formula for point load. So in 1885, around, Boussinesq developed the mathematical relation for determining the normal and shear stresses that are getting developed in the soil at any point inside what is called as a homogeneous, elastic, and isotropic mediums due to a concentrated point load which is located at the surface. So if you are looking at any surface here in geotechnical engineering, the surface what we are talking is your ground, okay, but it could be any surface. On that particular surface, if you have a point load acting, so due to that point load, how much is that stress what is getting developed in the medium what we are looking at. So here the medium is the soil what we are looking at. So it could be any other medium if you are referring to some other domains like in mechanical engineering or in some other aspects. So medium could be different. Here in geotechnical engineering, the medium what we are looking at is your soil. So for that soil which is assumed to be homogeneous, isotropic, and within your elastic limit, this Boussinesq went on to develop the relations for estimating the normal and shear stresses that are getting developed at a point in that particular medium. So that's the basis what we are going to be looking at. And the assumptions what he has made in deriving that particular expression is, as I mentioned, the material is homogeneous, isotropic, and elastic, and that particular material is extended to a semi-infinite depth. So in the depth direction to a semi-infinite distance, the material is extended. And what he has assumed is the soil, whatever we are trying to look at, is weightless. Okay, so he has not taken into consideration of the self weight of the soil in the estimation of your stresses due to that concentrated load. Already we have seen how to calculate your stresses due to the self weight of the soil. Now here what we are going to be understanding from Boussinesq's theory is only due to the external load, how much stresses are getting developed is what we are trying to understand. Then later on, what is your total stress that is getting developed in the soil means it is due to your applied external loading plus due to the self weight of the soil. A combination of that will give you what is the total stress that is getting developed in the soil at any depth or at any position in that particular soil medium. So the distribution of that sigma z, what does this sigma indicate? Sigma indicates the normal stress, and z indicates your vertical direction. Okay, so the variation of your vertical stress in the z direction within your elastic medium is apparently said to be radially symmetric. So if you are looking at your ground, and if this is your point load, generally this point load is what is otherwise also called as your axisymmetric loading. So why is it called as your axisymmetric loading? From that point of application of the load, if I look at in this direction or in this direction or in this direction or in this direction, as we said, the soil is homogeneous isotropic. So the intensity of stress, what we are talking about at a distance of 1 meter here or 1 meter here or 1 meter here, 1 meter here, or subsequently at a depth of z meters and subsequent radial distance of 2 meters, 2 meters, 2 meters, 2 meters in any direction, the intensity of stress what you are going to be coming across, or that stress what is getting developed, is considered to be same. The stress is infinite at the surface, as I mentioned, like just immediately below the point of application of the load, the stress what we are trying to understand, how much is it getting developed means it's almost infinite at the surface, directly beneath the application of your point load, and it tends to decrease with the square of the depth. So as you move into deeper and deeper depths, with the square of the depth, obviously, because in simple terms, the stress, as I mentioned, is nothing but P by A. So where this area is in turn what we'll be writing in terms of your depth at which you are trying to calculate that particular stress. So stress is going to be inversely proportional to the square of the depth. So automatically we understand that with increase in depth, automatically the stress what is getting developed is going to be decreasing. At any given non-zero radius, we'll understand what are these terms which we are talking about. So at any non-zero radius, let's say for example, this is my ground, this is the position of your point load, okay, intensity of the point load is P. So the axis of the loading, the line of action of that particular point load is like this. So at any radial distance, from the axis of the loading at any radial distance r, if you are trying to calculate the amount of vertical stress what is getting developed. Okay, so that vertical stress what we are going to be calculating from the point of load application, the vertical stress what we are going to be seeing immediately. Just say just below the point of application of the load, we said stress is going to be infinite, but on the soil grain which is adjacent to that particular particle, let's say this is particle A, this is soil particle B. On soil particle A, the amount of stress what is getting developed is maximum, but at soil particle B, the amount of stress what was getting developed was almost zero. Why? Because the load what you are applying was not at all getting transferred by any means onto that particular particle B. Okay, so at that non-zero radius, position of point B is something at a radial distance of something, let's say r. So at that non-zero radius, if you are trying to calculate what is your increment in stress or what is your stress that is getting developed at the surface, so that's nothing but it is zero. But as you move into the deeper depths, that value tends to increase, and then further as you move into furthermore deeper depths, that value further tends to decrease, and it is found to be maximum at an inclination of what is called as your theta is equal to 39.25 degrees. In that sense, this is that theta value what we are going to be referring to. So at that inclination of theta is equal to 39.25 degrees, you are going to see the amount of stress what was getting developed was said to be maximum, and beyond that, at any other depths, if you are going further, you would see the stress level in the vertical direction starts decreasing. So let's quickly understand that this is your point load what we are trying to talk about. This is your ground surface. Okay, so which you are defining it as your plane. This direction is what is referred as your x-axis. The vertical direction is what is referred as your z-axis, and direction perpendicular to the screen is what is considered as your y-axis. Okay, now the load what is getting applied, the case of case what we are looking at is a concentrated load which is acting in the vertical direction, that means in the z-axis direction. Now due to that point load what is getting applied on the ground, how much is the additional stress, or how much is the stress that is getting developed at point A in the vertical direction? That is what we are going to be calculating. So at that point A, at that point A, so how much is the stress what is getting developed in the soil due to a load what is applied at some other point? So load is applied on the ground. So due to the load what is applied on the ground, I want to calculate the amount of stress increment in the vertical direction at some point which is there at a depth of z meters below the ground surface. So I can go on to calculate that based on the Boussinesq equation, or based on the Boussinesq theory, we can go on to calculate that increment in stress in the z direction at any particular depth below the ground surface due to the load what was getting applied on the ground surface. So I suggest all of you should be remembering this particular standard expression what is given by Boussinesq. Okay, so what is this expression referring to? This expression refers to that of how to calculate that so-called stress which is getting developed in the soil at point A in the vertical direction. How much is that increment in stress at point A due to the load which was applied somewhere on the ground surface? Now where is this point A? Point A is there at a depth of z in the vertical direction, and from the axis of the loading, the point A is at a distance of is at a radial distance of small r. Okay, so the depth at which the point A is chosen from the ground surface is z, and from the axis of the loading, point A what you are trying to look at is at a radial distance of small r. Okay, so I understood the position of point A what I have chosen, and at that point A position, if I am required to calculate how much is that increment in stress in the vertical direction, I can go on to calculate from this particular expression what is given by Boussinesq. Okay, so it's a standard expression. We are not going into the derivation part of it, so please do remember this particular expression. Okay, so those are interested can refer to any of the standard textbook on our geotechnical engineering, where you would find this particular expression derived. Okay, where sigma z is nothing but the stress what is getting developed in the z direction at point A is equal to 3p by 2 pi z square. What does P refers to? P indicates the intensity of the point load, what is getting applied on the ground surface, and Z indicates at what depth that point A is chosen from the ground surface. And in this particular expression, if you look at R is indicated, small r. What does that small r refers to? At what radial distance that point A is existing from the axis of the loading. So that is what is called as your R, radial distance. Okay, or in simple terms, this particular expression can also be represented as sigma z is equal to P by z square into IB. What is this IB here referring to? IB here refers to that of what is called as influence factor. Okay, so in simple terms, what does this influence factor mean? Load is applied somewhere, but stress is getting developed at some other point. It's not that load is stress is getting developed only at the point where the load is applied. Stresses in the soil is also getting developed at some other points also, which need not be immediately below the point of application of the load. Okay, so this influence factor says that what is the effect of influence of that applied load at point A? What is the influence of the applied point load which is applied at the ground surface? What is the effect of this point load what is applied at the ground surface with respect to the position of point A? So that is what is called as your influence factor. Okay, so from the expression I can directly go on to calculate your influence factor, and accordingly I can go on to substitute. But however, you also have some standard tables, tables from which you can pick your influence factor value. You need not calculate and all. Okay, so if you know what is the radial distance at which your point A is there from the axis of the loading, and what is the depth at which that particular point A is chosen. So once that data is known, you need not go to that mathematical expression to substitute and accordingly calculate. You have some standard tables already available in your any of the standard textbooks if you look at. So from that, for corresponding R of so and so, Z of so and so, how much is my influence factor? I can pick it. I can substitute here to get how much is my corresponding increment in stress in the Z direction at that point A, what I am looking at. Okay, so that influence factor, what is that expression that is referring to? So in the earlier expression, except P by Z square, all the other remaining terms are simply what we are representing it as your influence factor. Now this particular stress expression for stress what we have calculated, if you can clearly understand, that expression is independent of the Poisson's ratio of the soil, and it is also independent of your elastic modulus or modulus of elasticity value of your soil, or the deformation modulus of your soil. So basically the expression what is given by Boussinesq is a function of the load, the depth, and the radial distance at which you are calculating your stress. So it should be noted that the expression for Z, or rather sigma Z, which we have calculated or which we have seen, which is given by Boussinesq, is independent of your elastic modulus value of that particular material, that's nothing but soil, as well as your Poisson's ratio value of that particular soil. So which means that the stress increase or stress decrease, or the expression for stress what you are trying to talk about, basically is dependent only on the geometry conditions. Geometry conditions in the sense, where is that point A? In the depth direction, in the radial direction. You are looking only in terms of the geometrical aspect, not your elastic property as well as your Poisson's ratio value of that particular soil. So as I was mentioning, like for different R by Z ratios, because if you know your R value and Z value in your expression, you can go on to understand what is your R by Z ratio. So for different R by Z ratio, you will have your different influence factor values. Okay. So if your R by Z ratio is 0.00, then accordingly your influence factor is something. If your R by Z value is something, you have your influence factor to be something else. So for different influence factor values, you have your different R by Z ratios, you have got different influence factors which are available from your standard tables, like this. Next, let us understand how does the stress distribution diagram is going to be? Like, how does the stresses vary due to that applied point load? How does the stress variation is going to be existing with the direction in the vertical axis as well as in your x or your y axis, what we are looking at. So ultimately, what I just want to understand is I am going to be talking about 3 pressure distribution diagrams here. One pressure distribution diagram is about how your vertical stress distribution is varying in a horizontal plane, and other pressure distribution diagram or the stress distribution diagram which I am going to be talking about is how your vertical stress is varying on a vertical plane. Vertical stress distribution, how is it varying on a horizontal plane? Vertical stress distribution, how is it varying on a vertical plane? And we are going to be talking about another pressure distribution or stress distribution diagram, which we are going to be calling it as stress isobar. What does stress isobar mean? Iso means same. Bar in the sense pressure, because bar is the unit for indicating your pressure. Okay. So we are going to be joining the points corresponding to the same stress. Okay, so by joining the points corresponding to the same stress, we are going to be indicating a kind of a bulb, which we otherwise also call it as pressure bulb, or that line which you are indicating by joining the points corresponding to the same stress value which was getting developed in the soil. Okay, so that line is what is called as a contour. In general, it's nothing but it's a contour, because in surveying we might have learned what is meant by contour. Contour is nothing but it's a line joining the points of equal elevation there. But here what is called as your isobar, I can also otherwise call it as your contour. Contour referring to the line the line what is formed by joining the points of your equal stress, same stress values. Okay, so let us understand how your distribution, your stress distribution is varying on a horizontal plane. Okay, so what is that we are referring to? Let's quickly understand by looking at something here. Yeah, let's say this is my ground. On this ground, you have some point load which is acting. Let's say the intensity of that particular point load is P. Where this point load, whatever we are trying to look at is, let's say, is acting at some point O. Now, I just want to understand how does the stress is getting developed at a depth of Z1 meters below the ground at different points. Okay, I repeat, I am interested in now understanding how the stress is varying in the soil, which is there at a depth of Z1 meters below the ground surface. So what is going to happen? Obviously, the stress is going to be maximum. Where is it going to be maximum? Along the line of action of that particular force, the stress value is going to be maximum. If you want, you can go on to calculate by making use of the expression what is given by Boussinesq, like 3p by 2 pi z square. Okay, complete expression may not be fitting in here, so I can simply write it as p by z square into ib. So from this expression, I can calculate z is nothing but z1, and what is my radial distance value for this corresponding point. Let's say this is 0.1, 0.2, 0.3, 0.4, and the other points on the other side 5, 6, 7. Okay, so now at this point 1 is at what radial distance? 0.1 is at a radial distance of r equal to 0, because it's lying on your line of action of that particular applied force only, from the axis of, on the axis of your loading only. Okay, so your radial distance r is equal to 0, whereas your z is to be substituted as z1. So for which I'll be getting some vertical stress value, which you are going to be having at 0.1. Likewise at 0.2. What is going to happen at 0.2? Z is nothing but Z1, and you have some radial distance. 0.3, radial distance further increasing. 0.4, radial distance is further increasing. What is going to happen? As you move into, as you move away and away from that particular axis of the loading, the intensity of stress what gets developed is going to be decreasing. Why is it going to be decreasing? Because the region or the stretch over which that particular point is there is far away from your loading position. So if it is far away, obviously that amount of load what gets transferred to that particular far away point is relatively less when compared to that of the amount of load what gets transferred to that of the points which are nearer to the loading region. Okay, so from that what I understand is, if I just want to plot the variation of your stress distribution diagram on a horizontal plane, this is my horizontal plane. What I am looking at is your horizontal plane. So at a chosen depth, I have some horizontal plane. On that horizontal plane, at different points which are marked on that horizontal plane, if I am trying to calculate how much is my vertical stress that is getting developed, so this is what it tells me. This is what I am calling it as your stress distribution diagram or pressure distribution diagram on your horizontal plane. Now what I know is, if this horizontal plane what I have chosen is at a depth of something z2 meters below the ground surface, then what is going to happen? As z increases, automatically the amount of stress which was getting developed in the soil decreases, which we have already talked in our earlier case. Okay, so but still, along the axis of the loading, the amount of stress which gets developed is said to be relatively more when compared to that of the other adjacent points. Okay, this point, once again, let me call it as 1 dash point. This is some 2 dash point. This is some 3 dash point. This is some 4 dash point. And likewise, on the other side, it is some 5 dash point, 6 dash point, 7 dash point. And if I just try to plot your stress distribution diagram, I might have my stress distribution diagram something like this. Now, if you clearly understand, earlier when I have talked about your stress distribution diagram on a horizontal plane which is chosen at a depth of z1 meters, the intensity of stress was more. As you moved into the deeper depth, the intensity of stress that was getting developed is relatively decreasing. And furthermore, deeper, if you are referring to at a depth of z3 meters below the ground, the intensity of stress further gets decreased, and you might be seeing like this. And furthermore, if you are going ahead, so you will see that intensity of stress is further getting decreased, and so on. This is what is called as your stress distribution diagram for that applied point load on what is called as your horizontal plane. We are understanding how your stress distribution diagram is varying when your applied load, due to that applied load on a horizontal plane. Now, in similar way, if I just want to understand how your how your stress distribution diagram is going to be varying for the loading what is applied with respect to that of a vertical plane. Let's say this is my ground on which you have your point load. The intensity of the point load is P. The point where that point load was acting is O. This is your axis of the loading. Now, on some vertical plane, let's say I am choosing some vertical plane which is there at a radial distance of something R. Earlier, horizontal plane at a depth of some Z1 or Z2, something we said. Now, I am talking about a vertical plane. From the axis of the loading, I am referring to a vertical plane which is at a radial distance of something R, R1, R2, whatever. Now, if I start understanding how much is my amount of vertical stress that was getting developed at this point. So, yes, the point what I have marked, let's say this is some 0.1, this is some 0.2, 0.3, 0.4, 0.5, and so on, if I am looking at. So what we understand is that at 0.1, obviously the stress what was getting developed is going to be 0 because the load was applied at point O, and to 0.1, there is no load transfer happening. So that's the reason why the amount of vertical stress that was getting developed at 0.1 is nothing but it is equal to 0. But as you move into deeper depths, what we understand is the amount of vertical stress that was getting developed increases, and beyond some particular depth, what we see is that the amount of stress which was getting developed at further deeper depths continues to decrease. Okay, so this is what is called as your stress distribution diagram or the pressure distribution diagram on a vertical plane, where your vertical plane is chosen at some radial distance R. Let's say radial distance of something R1. If you are choosing your vertical plane at a radial distance of something, let's say R2, Okay, so how is your pressure distribution diagram going to be? So what happens is your intensity of your pressure or intensity of the stress starts getting decreased with increase in your radial distance, and likewise at further radial distance, if you are looking at how your stress distribution diagram is going to be, so intensity of the stress further tends to decrease. Yeah. Coming to the third one, that's the other pressure distribution diagram, which I said, which we'll be talking about. It is nothing but we call it as your stress isobar. Okay. As already I mentioned, so isobar is nothing but it's a line which connects all points of equal stress below the ground surface. So in other words, an isobar is also called as your stress contour. Okay. So at different points below the ground, the point here, point here, point here, point here. So at some points below the ground surface, you had the same intensity of stress. So all those points we are trying to join, and the corresponding line or contour what is getting formed is what is called as your isobar, or otherwise we are calling it as your stress contour. And this is another stress contour. This is another stress contour. So stress contour corresponding to different intensity of stresses. So all those points you can try to join, and they are otherwise what is called as your stress contours. Or this is what I can also call it as your pressure bulb. This bulged section or whatever shape that we have drawn is what I can also call it as your pressure bulb. Okay, so here are some of those examples which you can take it up. These are your direct examples. We don't have something technicality involved in solving it. So you have 2 point loads acting on the ground, and due to those 2 point loads, we are required to calculate how much is your vertical stress that is getting developed at point A, which is there below the ground. Okay, so that point A is chosen at a depth of 2.5 meters below the ground, and you can accordingly calculate how much is going to be your increment in stress. But you should understand that total stress what was getting developed because of your 2 point loads at that depth of z equal to 2.5 meters is nothing but I'll write it as sigma z1 plus sigma z2, where this sigma z1 is due to your load 470 kilonewton. Sigma z2, what I am going to be calculating, is going to be due to your load, which is 350 kilonewton. So due to 350 kilonewton, first I should individually, because of your individual point loads, I should calculate how much is your vertical stress developed at point A due to load 1 as well as due to load 2. And due to both the loads, if I want to understand how much is your vertical stress at point A, I should be adding the effect of those 2 loading conditions. So likewise, you have another particular case where you have 4 concentrated forces acting on a rectangular represented area. Okay, and you are required to calculate the amount of vertical stress at points A and B, which are located at a depth of 4 meters below the ground surface. Okay, so where this point B, if you look at, is the projection of your point B dash in the vertical direction. Where this point B dash is existing means at the center of that particular area of 8 meters by 4 meters. And whereas your point A, which is vertically projected from the position of this point A dash, which is one of the corner of that particular rectangular represented region. Okay. So please do go on to solve this particular problems. If you have got any difficulties, you can revert back to me by writing a mail, or you can drop me a message if you have got difficulty in solving it. Next, moving on to understand how to calculate your vertical stress, because earlier we were trying to talk about, we said we'll be discussing on how to calculate your vertical stress because of your concentrated load or point load, both by Boussinesq theory as well as your Westergard's theory. Okay, so earlier whatever expression we have seen is based on your Boussinesq theory, how to estimate your vertical stress, okay, due to your applied concentrated loading on the surface. Now let's quickly understand, due to your Westergard's formula or Westergard's theory, how do we estimate your vertical stress. So before we go on to see what is the expression given by Westergard based on this based on his theory, so let us quickly understand what are the assumptions that are made in Westergard's theory. The soil is considered to be elastic and semi-infinite in depth. Soil is composed of numerous closed-spaced horizontal layers of negligible thickness of an infinite rigid material. The rigid material permits only that so-called soil, whatever we are trying to look at, is assumed to be considered as negligible thickness layers and which are said to be relatively rigid in nature. So rigid in nature in terms of the horizontal direction. So which means that your so-called deformation, whatever is happening in that particular semi-infinite layer of soil, the deformation is happening only in the vertical direction. There is no lateral deformation happening in such particular soil material. Deformation in X direction due to the applied load and deformation in the Y direction due to the applied load is what is considered to be zero, whereas your deformation due to that applied load is expected to be happening only in the Z-axis direction. These are your assumptions in your Westergard's theory. Based on that assumptions, Westergard developed an expression for estimating the stress in the vertical direction, and this is the expression what Westergard has given, which we will be calling it as Westergard formula, based on which we can go on to calculate how much is that vertical stress which is getting developed in the ground, which is at any point. Let's say here also we are trying to consider a point A. So where this point A is at a depth of Z meters below the ground surface and at a radial distance of something small r from the axis of your loading. So where the expression what Westergard has given is P into A by 2 pi Z square into A square plus R by Z whole square whole to the power of 3 by 2, where P here refers to that of your concentrated load, what you are applying, and A, small a, whatever we have here, is once again a function what is given like this, where A is equal to under root of 1 minus 2 mu divided by 2 minus 2 mu, where mu here refers to that of Poisson's ratio of your soil. Okay, based on this particular expression, we can go on to calculate how much is your vertical stress that is getting developed in the soil. So here, what data we will be requiring is at what depth that point where you are calculating the vertical stress is existing, that point at what depth it is there from the ground, that depth should be known. What is the radial distance from the axis of the loading at which that point what you have chosen is existing. So that R value, small r value should be known, Z value should be known, and the Poisson's ratio of that particular material in which the deformation is happening, that's nothing but the Poisson's ratio of the soil, should be known, and obvious that the intensity of the concentrated load or the magnitude of your concentrated load should be known. So once that is known, you can go on to substitute into this expression what is given by Westergard, and we can calculate the stress what is getting developed in the Z direction at any position below the ground surface. And now coming back to the other loading conditions, whatever the expressions that we are going to be subsequently seeing are once again given by Boussinesq only. Okay, so as I said, because of a line load, what we have earlier seen is because of a point load. Now because of a line load, how do we understand this particular line load? Line load is nothing but it's a combination of your point loads only. If you look at here, the represented loading, so the load is acting along a line which is extended to some infinite distance, let's say. Infinite doesn't mean it is infinity, okay, to some maximum distance. When you look at a railway track, this is one rail, this is the other rail, okay. Rail continuously goes on. You will see the rail at the track which is extended to an infinite distance. That is what we say. The load which is coming from the wheel of your train is what is assumed to be considered as your line load, because load is continuously getting applied on one of the rail, because wheel will not directly come in contact with the two rails. It will act only, the wheel will be rolling only on one rail. Similarly, I have another set of wheels which are rolling on the other rail. Okay, so that load what is coming from the wheels of your train on individual rail, so that loading is an example for your line load. So how do we analyze this particular case means? So same whatever we had which is given by Boussinesq. Okay. So in similar way, this expression is also derived. So Boussinesq first developed or derived the expression for point load. Here what we have is series of point loads existing in a line. Okay. So what we can do is the earlier expression, you can go on to integrate it over the length over which that particular series of point loads were getting a series of point loads were acting on the ground surface, and the expression what he has given is sigma z is equal to 2 into q into z cube by pi into x square plus z square whole to the power of 2. Okay. So what does this x square mean? As it is a line load now, the loading cannot be considered as axisymmetric in all the directions. If you are looking at the loading, you cannot consider it as symmetric. Okay. So that's the reason why the so-called radial distance at which you are now point A, what we are trying to choose here below the ground surface, which is there at a depth of z meters. So at a radial distance in the sense in the x direction now particularly. Okay. So in the x direction, the point A is there at a distance of x, some small x. And Q here refers to that of your intensity of that line load. Okay. So the intensity of that line load is what we are calling it as your small q. Okay. So based on this expression, we can go on to calculate, because of your line load what is getting applied on the ground, how much is your increment in stress at any particular depth. We can still go on to calculate from the expression what we have here. So in similar way, if you the earlier example of loading what we were looking at is your line load in the vertical direction. In case if your line load what we are trying to talk about is in the horizontal direction like this, if this plane, if I am just trying to extend it, so I have a series of point loads which are extended in this horizontal direction. That means in the y-axis direction. Okay. So for that horizontal line load condition, if I am required to calculate how much is your vertical stress that was getting developed at any point what you have chosen below the ground, so I can make use of this particular expression from which I can still go on to calculate the increment in stress or the stress which was getting developed in your ground. And next, moving on to understand in the case of your strip load. Strip load is something, an example of the foundation related to that of the compound wall. As I said, when you look at your compound wall, this is your wall below which you have the base for your compound wall, and on the bottom of this compound wall, where this compound wall is resting, this compound wall is going to be resting on a soil strata. Okay. Load comes from the compound wall, gets distributed over certain width of this foundation, and if you understand, the compound wall extends, or you will be seeing the compound wall continuously running to a maximum length in the direction perpendicular to the screen. Okay. So such kind of load which is acting over certain width and extended to some maximum distance in this y-axis direction or in the direction which is perpendicular to the screen. So such kind of loading is what is called as your strip load, or that particular footing from this from which this load is coming is what is called as your strip footing. Strip footing in the sense where the width is limited, the length is relatively very large. So this is the typical strip loading what we are trying to talk about. Okay. So loading in this direction is continuous, but where the load is acting over a limited width. Okay. So in such particular case of your strip load, if we are required to calculate how much is your vertical stress that is getting developed in the soil strata, so we have an expression which is given by Boussinesq, something like this: Q naught by pi into alpha plus sine alpha into cos of alpha plus 2 beta. So you can clearly understand what does this alpha angle indicate, what does this beta angle indicate from the figure which is given here. And Q naught indicates the intensity of your strip load. Okay. So Q naught here indicates what is called as Q naught, or simple Q. What is indicating here is nothing but the intensity of your strip loading which is acting on that particular ground surface. Here you have one example what is given with respect to that of your strip loading condition. So it's a straightaway case. So you can simply go on to substitute your values into that particular expression to calculate how much is your amount of vertical stress which was getting developed at different points which are given here, point A, point B, and point C. You know the position of point A, you know the position of point B, you know the position of point C. So accordingly, you have to understand how much is your alpha value, how much is your beta value. And once you know your alpha value and beta value, then you can simply go on to substitute into that expression by knowing what is your Z value which you are looking at and intensity of your strip load, what is given here in this particular case. So your strip load is given as 120 kilopascal. So once the strip load is known and Z values which are already known, only thing what you should be clearly understanding is with respect to point A, how much is your alpha angle and beta angle? With respect to point B, how much is your alpha angle, beta angle? With respect to point C, how much is your alpha angle, beta angle? And upon substituting, you'll be getting how much is the increment in vertical stress with respect to different points which are existing below the ground surface due to a given strip load. Okay. So with this, we'll stop our discussion for today, and we'll be continuing our discussion in our next class.